I'll be telling you kind of a pretty high-level view of lattice-based cryptography. This is one of the most, in my opinion, the most promising source of post-quantum cryptography that's hard against quantum computers, but that we can run on today's classical, ordinary computers. We don't need any quantum magic to run it. So the kind of outline and what I'll be talking about, not in full linear order here, but the basic things you can expect to learn about are the basic foundations of modern lattice cryptography. And these include the SIS and LWE problems. You may have heard one or both of those. And some of the basic applications, cryptographic applications of those problems. And those are sort of the foundation on which all kinds of other very cool cryptography has been built. And then toward the end, we'll get into making this more efficient, the kind of main ideas behind how these can be made more efficient at a potential difference in security using what are known as rings for efficiency. And I'll briefly mention, as we go along, some practical instantiations of this work. So what's really cool about this work, this whole big field, is that in the last 25 years or so, it's gone from being like a very kind of inefficient theoretical curiosity to being something that's actually deployed in practice and can be run in reality on real networks. And in fact, just earlier this month, NIST, the National Institute of Standards and Technology, decided, they announced what their post-quantum cryptography standards will be, and that includes 3 of these 4 systems right here. So we'll talk about kind of the main ideas behind them. And then along the way, I hope to bring up many interesting open questions, research directions, all of which I think would make a good paper, some of which might make a good PhD thesis, and some might make a career, okay? So hopefully we'll give you some good flavor there. And you may have a handout in front of you with some exercises. Don't expect you to be able to do these exercises now. By the end of the talk, and then with a few hours of effort, you can probably do it. Or if you're feeling very ambitious or very bored by my talk, you can start working on them right away. Okay, so that's the agenda. And let's jump in for the next 85 minutes or so. Oh, by the way, if you have questions, please interrupt. Just hand up or yell or whatever you like. There's plenty of padding, to answer questions and make sure everybody's getting what they need out of it. Okay, so we'll start with the foundations. This is the SIS. You will learn what that means. And then some basic cryptographic applications, hashing and digital signatures. So the basic idea behind lattice cryptography is, for 40 plus years, we've been using number theory like factoring and discrete logarithms and pairings, exotic things like that, to do cryptography, to allow Alice and Bob, the proverbial Alice and Bob, to communicate securely with each other in the presence of an attacker. And lattice-based cryptography says, well, that was nice, but let's do it a different way. Let's use hard problems on these geometric objects called lattices instead as the foundation for our cryptographic protocols and procedures. Okay, so the hardness and the security of these crypto systems will come from the hardness of lattice problems. Okay, so why should we want to do this? I mean, everything was working fine, right? Like, why break what isn't broken? Well, first of all, the systems that you get are really interesting in that they're asymptotically very efficient. All the operations are small and parallel and linear, and you can implement them very easily in very low depth and with small operations. So we'll see what that looks like. In contrast to all the other math that I had just shown, which is all breakable by sufficiently powerful quantum computers, as far as we know, these systems resist quantum attacks. Okay, so that's why they're so-called post-quantum. One of the really interesting theoretical benefits of lattice cryptography is that you can get security from what are called worst-case hardness assumptions. And I'll say a little bit more about this, or a lot more about this, actually, in the coming slides. But basically, it means that in order for your cryptographic scheme over here to be secure, and it needs to be secure on the average, right? It needs to be secure for almost every choice of key or ciphertext that you might produce. All you need is for the problem over here to be hard in the worst case. Okay? It doesn't need to be hard for average, for randomly chosen objects, as long as some small, maybe very rare class of instances over here are hard, then nearly every instance over here that you might choose randomly is hard. Okay, so that's a really it's a unique property of lattice-based crypto that other systems don't get in the same kind of way. And then making cryptographers really excited also is that we can get solutions to these so-called holy grail problems, like fully homomorphic encryption and holy grails we didn't even know to think of before we solved them, right? So holy grails are being found all over the place now, thanks to lattices. Okay, so let's get into some formal definitions and background. So a lattice you can think of as just a periodic grid and in Euclidean space. And for the purposes of today, we'll just consider integer lattices. Okay, so it's a subset of the integers to the mth power, right? The m-dimensional integers. So over here, I just have the two-dimensional integers, which is this ordinary square grid. And then the lattice is the set of green points in here, which is periodic, or more precisely, it's an additive subgroup of full rank. So you can take any two lattice points, this one, and add them together, you'll end up with another lattice point. And then you can also invert a lattice point. So you take this lattice point, you can take its negation, and you end up with this lattice point here. Okay? And so, I mean, I didn't show all of it because I just have a small screen, but this lattice goes out forever periodically. Right? Okay, so that's what a lattice is for our purposes today. And this is a two-dimensional lattice. Just think of like a several hundred-dimensional lattice instead, okay? Because that's where we'll be living. Right? No problem? Everybody got that? Okay, good. So those are pretty hard to visualize, and intuition is hard to come by. But fortunately, we have math to help us. Okay, so a lattice is an infinite object, but it can be represented finitely by what's called a basis. So a basis is just a full rank generating set of vectors. So it's a set of vectors that are linearly independent, which generate all the lattice points as the integer linear combinations. Okay, so if you take b1 and b2, and you take any integer combination of them, like b1 plus b2, you'll end up with a lattice point. Or you can get up here, which is, I guess, twice b2 plus b1, something like that. Right, over here, anyone know what this one is? How do we write it in terms of the basis? Yeah, b1 minus b2, right? So we go out to here, and then we subtract b2, and we end up here. Okay? So just all these integer combinations give us exactly the points in the lattice. Okay, so this is a nice-looking basis, pretty nice. But there are other bases of the very same lattice. So this b1 and b2 here, you'll notice they generate the same lattice, proof by a picture here, right? But it's true, right? It's just a little bit weirder. These are longer vectors, and they're kind of more squished together, right? But yet they still generate the same set of points. And at a very high level, this is exactly the kind of thing that makes, or that allows lattice problems to be hard. So we'll get into that. Okay, so a basis is one way of representing a lattice. We'll see another way of representing a lattice in a slide or two. Okay, so any questions about this so far? All right, so pretty basic stuff. You may have learned it in high school or elementary school, depending on. So we need hard problems to do cryptography. And there are many, many problems that seem to be hard on lattices. They almost all have the nature that they're all related to somehow finding short vectors or detecting short vectors or decoding from short vectors in the lattice. So I'll just give you one particular example. The most famous problem is the shortest vector problem. And it says, I give you a basis of some lattice, and the goal is to just find a shortest non-zero vector in the lattice. Okay, so here is an answer to the shortest vector problem, right? You give me this basis b1, b2, and you have to produce this value, which is, I guess, b1 minus twice b2, right? Or you could produce this one. It's also just as short, just the negation, right? So that's the shortest vector problem. It asks for an exact shortest vector. But for cryptography purposes, we don't need to be exact all the time. Frequently, we're not exact. We have this approximation factor gamma here. And the gamma relaxes the set of what are considered to be solutions. Okay? So SVP gamma says, find me a non-zero vector whose length is within a factor of gamma of the shortest. Okay? So if we say that gamma is 2, for example, then these original points are shortest vectors, so those are good solutions. But these two up here would also be good solutions. They're a little bit longer than the shortest, but they're within twice the distance. Yeah? Gamma doesn't have to be an integer. You could, root 2 or root n or whatever you like is just a real number. And sometimes, frequently, in fact, it's a function of the dimension. So yeah, as I say here, if you take gamma to be some polynomial in the dimension, m squared or m to the 5th or something like that, we don't have any good way to solve these problems efficiently. Okay? So the best algorithms that we have require exponential time and memory, even quantumly. So even with the help of quantum computation, we don't know how, despite a lot of efforts, we don't know how to get polynomial approximations to SVP within, in better than exponential time in the dimension. Okay? So this is really kind of the curse of dimensionality is what's making these problems hard, and it's why we need to work in very high dimensions in order to make these kinds of runtimes meaningful, right? Meaningfully infeasible. Okay. Any other question about this so far? So when you think about lattice problems, the canonical one to keep in mind is just given a basis, find a vector that's nearly as short as possible, up to some relaxation factor. Okay, so that's the definition. And now I'll give you your first cryptographic problem. And the first exercise on the paper is also about this problem. It's kind of toying with this problem. And the problem is called SIS, or short integer solution. This was defined in the seminal work by IPAM in 1996. Although the problem itself kind of goes back even farther. It looks a lot like subset sum, and it's got a long kind of pedigree. Okay, so here's the problem concretely. So I'm going to define a zq to the n just to be the set or the group, the additive group of n-dimensional vectors with integer entries, and all the arithmetic is mod q. So when I add vectors together, it's the usual way, except I always reduce the integers mod q when I add them. Okay. So here's the problem. The input to the algorithm is a sequence of uniformly random vectors in ZQN. Okay, so these are just uniformly random vectors, n-dimensional vectors, mod q entries, 1, 2, 3, 4, m, up to some m of your choice. Okay. And the goal, given this input, is to find some non-trivial integers z1 through zm, which are ternary, so they can be 0 or plus minus 1, so that this kind of plus minus or 0 combination of the A vectors adds up to 0 modulo q. Okay. So that's the problem. Given this input, and let me emphasize that input is uniformly random. So everything, I don't know if you can tell the colors here, but in blue throughout the talk will denote uniformly random. Right? So this is an average case problem. You can rely on the input being random. That may help your algorithm work, some 1% of the time or whatever, right? That's all fine. But you have to find these vector of these z's, okay, that cause these to add up to 0. So it's kind of, yes. Yeah, it's not completely obvious that there's always a solution. In particular, if m was 1, okay, so if you just had this, there would almost never be a solution. But we'll see in a moment, there is always a solution as long as m is large enough, roughly n log q or so. We'll see why that's the case. Yeah, but that's the first thing you should ask. Like, is this a rigged game, right? Is there even a solution? And in fact, just take m to be moderately large, and it guarantees a solution exists, regardless of what the a's are. Okay? So in order to avoid like a whole bunch of pluses and vectors and everything like that, we're going to collapse this down to a little bit better notation. And I'm just going to write this as a matrix vector type of thing, right? So I'm going to put these columns A1, A2, AM into a matrix here, whose columns are the AIs. And then I'm looking for a vector Z, which is non-zero, such that A times Z equals 0 in the group CQN. Okay? That's a much nicer way to write it. I hope you agree. OK, so given this matrix A, uniformly random, find a non-zero vector Z with ternary entries. And in fact, you know what? I'll make it easier for you. They don't have to have 0 plus minus 1 entries. Just make sure the norm of Z, the Euclidean norm, is smaller than some bound beta. Okay. Right, so we're going to require that this Z's norm is less than beta, and beta you can think of as substantially smaller than Q. OK, so if you know of an algorithm to solve this, or you've thought of one in the last 3 minutes, please tell me. OK, it's very important. Because this is a problem that we base like all of the lattice cryptography on. OK, so if this problem's easy, you've ruined my entire career. OK, so good luck with that. I won't be mad, I promise, if you break it. OK, so let's see what we can do. We'll do the most basic construction of a cryptographic object here, which is a collision-resistant hash function. John, did you cover collision-resistant? OK, so I'm going to define a collision-resistant hash function. It's a real simple object. I give you a function from a family. So there's a family of functions. I choose one at random, and I tell you, find me 2 distinct inputs that map to the same output. And that's called a collision, right? So just find me 2 inputs to the function whose output that map to the same output. Right? And these are used all over cryptography. So we would really like to have a nice, secure, collision-resistant hash function. And here's how we can build one, assuming that this SIS problem is hard. Okay, so here's what we'll do. We'll set m to be strictly greater than n log q, as you asked. And now I'm going to define a function f sub a. So the matrix A is this matrix here. Right? So once we choose this function A, it defines the function fa. And fa is from the m-bit strings to zq to the n. Okay? And, OK, so why did I use this condition? Anyone see why? Yes? Yeah, it'd be trivially collision resistant in that there are no collisions because there's more outputs than inputs, right? So that would not be a very useful function. I didn't mention before, you want your hash function to compress, right? You want the more inputs than outputs, right? So doing this, we have 2 to the m inputs, which is more than 2 to the n log q, which is more than q to the n. That's the size of this. OK. So this is a compressing function, and the function is super simple. It's what we've already written up. It's if fa of x is just a times x. Okay, mod q, always mod q. All right, so that gives you this output. So it maps many large input to small output. And the claim is that this is a collision-resistant function. Okay, the proof is 1 line, 1.5 lines, and we can see it here. So suppose that I give you the function fa. I choose a uniformly at random, and the adversary, maybe you in this case, but some adversary is able to come up with a collision, right? So collision is distinct x and x prime from the domain, such that ax equals ax prime. Okay? And now I should have given this as like problem 0. Okay, what is the implication? What can we do here? So how do we use this collision to solve SIS? Everybody raise the hands. Yeah. Okay, all at once. Subtract. OK, x minus x prime, right? So the claim is that this z, which we'll call x minus x prime, is a short solution to our problem, right? OK, let's just check the requirements. X and x prime are different, so the z is non-zero. That's important, right? If z was 0, it would be a trivial solution. It's not 0. X minus x prime, you can check is ternary, because each of x and x prime is binary. So when you do the subtraction, the result is always in 0 plus minus 1. And have we done it? That's it, right? Oh, and by linearity, a times x minus x prime is 0 because of collision. Right? So all 3 things that we needed to happen, and we have it. Yes? Sorry? Oh, how do we check short? Right, so so we know the entries of Z are ternary. And so the Euclidean norm of Z is at most square root m, right? Because every entry has absolute value of most 1. So we'll just set this beta to be square root m. So yeah, this tells you, there's always some like wrangling of parameters in the end to make sure it all works out. But you basically make sure that Q is substantially larger than root m. And now, you know, the whole argument goes through. OK? Any question about this? It's pretty kind of basic warm-up stuff. Yes?
Is Q supposedly very large then?
You don't have to take it to be very large. For example, it would suffice to take like m squared, something like that, right? We just need this to be, there's a polynomial gap here that you need, right? So yeah, in fact, what's interesting is unlike probably every other cryptography you've heard of, where you work modulo a very big number, okay? Here we work modulo a Q that's, I don't know, 32 bits or something like that, right? Like pretty small, it fits on a word size of a computer. But there are a lot of them, right? We're working with vectors of small numbers, right? So the hardness kind of comes from simultaneously satisfying all this equation at once. Yeah.
Do people think about other norms?
Yeah, absolutely. So you can prove things about, you know, or you can use things about infinity norm here, right? We could restrict Z's infinity norm to be at most 1, right? This proof still goes through. For other applications, it will be much more useful to restrict just the Euclidean norm. Or you could restrict the Hamming norm, right? Or the L1 norm. I'm sorry, not the Hamming norm. That's a problem. But the L1 norm, for example. Yeah, so you can definitely work on those. And of course, all these LP norms are sort of the same up to a polynomial factor in the dimension. And today, we're all among friends, so we don't really care about polynomial factors. Okay. All right. So yeah, other questions about this one? OK, so there's a little exercise, or a few exercises to think about this problem here. What I want to show you now is, well, what does this have to do with lattices, right? Like I said this is supposed to be about lattices. There's no lattice here, or is there? Right? So here is a way in which this SIS problem is and really is very usefully seen as a lattice problem. Okay? So this matrix A that we pick this random matrix A, and you can use it to define what's now known as a Q-ary lattice, or a mod Q lattice. And this lattice is simply the set of all integer vectors in the kernel of A. Right? So AZ equals 0 mod Q. And that's, again, this is without regard to the norm of Z. Okay, so we don't care about the binary, ternary, short, whatever condition. Any integer vector satisfying this will be in the lattice. So it would look something like this. There's an infinite kind of discrete kernel here. And it's Q-ary in the sense that it's periodic. Like it's like this big brick, okay, this cubical brick just copied infinitely many times. And the brick has edge length q. So if you think about z here as a two-dimensional vector, q comma 0 is always in this lattice, right? Because you multiply the first column of A by q, that zeroes it out. The next column you multiply by 0, that zeroes it out. Add them up, you still have 0. Right? So these points, you know, q times the standard vectors are all in the lattice. And what that implies is the lattice is this kind of, as I said, shifted cube copies of the same thing. Okay? So what does this have to do with SIS? Well, if we now say you have to find me a short solution, a short non-trivial solution to AZ equals 0, what we're really asking for is find me a solution that's, you know, inside this ball, what the ball of radius beta, right? Whatever your norm constraint is. You're saying find me a solution in this ball. And that's really just like find me a short vector in this lattice defined by A. Okay. So the SIS problem can be rephrased as find me a short non-zero vector in this lattice L perp A. Okay. With no change in meaning, just different notation. Okay, so that's why it's a lattice problem. But there's an even more interesting reason that this is related to lattices, which is ITAI's famous worst case to average case reduction. Okay, so what ITAI proved and has been improved in many facets since then, but the nature of the statement is always the same. And it says the following, that the ability, or if you can find short non-trivial vectors in this random lattice, right, for a uniformly random A, and even with just some noticeable probability, 1% or 1 over polynomial probability, the ability to solve this problem implies by reduction the ability to solve these lattice problems in the worst case, that is on any n-dimensional lattice. Okay, so because we believe, because we have very good reason to believe that these problems are hard, very hard, even quantumly, that is then the evidence, or the reduction tells you that this problem must be hard as well. Right? Because if you could solve this problem on the average, you can solve these problems in the worst case, and we don't think that's possible. Okay, so in effect, what we have here is a kind of hardness for random lattices, right? We said that this finding short vectors in these random lattices L perp A is kind of informally at least as hard as finding short vectors in arbitrary n-dimensional lattices. Okay, so great result, brilliant, kicked off this whole field. It's really lovely theorem. I will not give you the proof. It's very technical and involved, but by now it's not that bad. I don't want to scare you away from it. I can point you to the proof if you'd like to see it. It's been made quite nice by now. All right, so any questions about just the meaning of this statement or the implications? Right, so L, are you asking about the L or the perp? Oh, yeah, yes, and hold that thought, because in about, 7 slides or so, you'll see that too. Okay, so this is the L perp, it denotes the kernel of A, basically, and then we'll have something else later. Okay, so this is good. Let's see a more kind of exotic application of this SIS problem. Not just collision resistance, but building digital signatures, right? John, did you cover digital signatures? Beautiful. Okay, so everyone remembers, because John did a really nice job telling you about digital signatures, so I won't have to remind you of anything, but I might remind you of something. Okay, so here's how we want to get a digital signature scheme. Let's say that Alice is the one who's wanting to sign documents or sign messages, right? So Alice has to generate a public key and then a secret signing key. Okay? What she will do is she's going to generate a uniformly random matrix A, so our old handy matrix A, as her public key. But she's going to do it in a certain special, clever way where she knows a special trapdoor about the lattice A, or the L perp A. She's going to generate it basically with knowledge of short vectors in the lattice L perp. Okay? So I won't tell you precisely how that's done. It's a clever algorithm, but you can think of it as analogous in like factoring-based crypto or RSA to saying, okay, I'll take 2 primes randomly and I'll multiply them together, and my public key will be the product, and my secret key will be the 2 primes. Okay? And very loosely, this is the kind of thing that Alice does as well. She generates a bunch of short vectors, and then she kind of munges them up and ends up producing a lattice, which is represented by this A. Right? So given this A, it's hard to find short vectors in the lattice, but she has prepared it in such a way that she knows short vectors by construction. Okay? So that's what her trapdoor T is going to look like, roughly. Okay, so when she wants to sign a message, she's going to use her secret trapdoor, and the message, we'll call it mu. Doesn't really matter what it is. But what she's going to do is put mu through a special kind of random oracle hash function. So it just puts it through a complicated hash function. And then she uses her trapdoor to randomly choose a short solution to AZ equals the hash of mu. Okay? Yes. Oh, yeah, great. So this is just like full domain hash. If you remember full domain hash, you take your message, you hash it into sort of the range of your trapdoor function, and then you invert. Okay? And that's basically what we're doing here, but with this very important ingredient that the inversion that we're doing here, so inverting and finding this preimage z, is done in a randomized way. Okay? So we're going to choose from a very specific distribution, and for a very good reason. So in particular, what we'll do is randomly draw z from a distribution that leaks no information about Alice's secret key. Okay? And my favorite one, the one that's most nice, is to use something called the discrete Gaussian distribution. Okay, so what is that? I've drawn now, all right, we're going to upgrade from 2 dimensions to 3. I hope you're comfortable with that, all right? Everyone's familiar with 3 dimensions. The lattice you can think of as lying on the plane here, this flat plane, and then I'm going to assign Gaussian probability to every point. So I'm assigning a Gaussian probability mass to each potential solution z here, and then I'm sampling at random from that distribution. Okay? So I will state without proof or justification that there is an efficient algorithm that allows you to do this if you know a trapdoor, a suitable trapdoor. So using this trapdoor T, we can sample from this discrete Gaussian distribution over the set of solutions, and then we will put out that z as our signature. Okay? So yeah, just like full domain hash, but with a randomized inversion procedure for mysterious reasons. Okay. Well, no, not mysterious reasons. The reason is that we do not want to reveal anything about our secret key. We don't want to leak any knowledge about it. And this is important. Earlier attempts to build digital signature schemes from lattices were basically all broken by this exact feature that the signatures leaked information about the secret key, and you could actually do some learning algorithm to recover the secret key after seeing a number of signatures. Okay, so it's really important that we do it in this way, or in a manner, in this kind of manner, because it's usually broken otherwise. Okay, so that's how we generate a signature. We sample a random z such that az equals the hash of the message. Okay, so how does one verify a signature? So Bob has Alice's public key. He has a message that Alice has signed, supposedly, and he wants to check that really Alice did sign it. So to verify, yeah, we have the public key, the message, and a purported signature. Well, all we have to do is check this equation. Right? We just check that AZ is the hash of the message. And then we'll also check that Z is sufficiently short. And by sufficiently short, we mean just, when you sample from this distribution, you're extremely likely to get something, as you can see here, the effective support of this distribution is inside this region here. And so we just check that the Z that's been provided is really in within that norm bound. Okay, and that's how, as long as both of these checks pass, you say, yeah, that signature looks legitimate. Otherwise, you would reject it. Okay. So any question about this? Yes. Mm-hmm. Oh, yeah. How do we generate A together with this trapdoor? I didn't tell you how to do it. It's complicated. But it's not that complicated. It's moderately complicated. Yeah, we'll see that next. Mm-hmm. Yeah, so I haven't said anything about security. I just want to make sure the mechanics of this scheme are clear enough. Yeah. And I have abstracted away the generating the trapdoor, and I've abstracted away this sampling algorithm. But otherwise, it's all that you see here. Okay. Was there another question about this one? So my claim is that you can prove the unforgeability of the signature scheme in just, well, the 2 lines or so that we have left on the slide. So the idea is that if you want to, you're a forger, you have seen Alice sign many messages, maybe messages of your choice even, and then you want to create a forgery for some new message, mu star. Okay? So what do you have to do? Well, whatever your new message mu star is, you have to come up with some short z star such that a z star is the hash of mu star. Right? That's what's necessary. In order to forge, you have to trick the verifier into accepting. Right? But my claim is that this is exactly the SIS problem. Okay? The public key is a uniformly random matrix A. Mu star is new. It's not something that you've seen a signature for before. So when you hash this, you're going to get some uniformly random target vector. And in order to create a good-looking signature, you have to find a short z star such that a z star equals that random target. Okay? And this is exactly the SIS problem that we've seen. Well, not exactly, but you can make it exactly. I think it might even be an exercise on the sheet. Okay? But if you think about it, you can see that indeed this is equivalent to or at least as hard as SIS to solve. Yes?
The hash function is a random oracle.
Yeah, the hash function is random oracle. Yeah. And that's really important for this argument, right? Because we're saying you have to hit a random target that you really have no control over. Right? So that's why the random oracle, it's one reason the random oracle helps. The other is when you turn this into a full proof, you need to kind of program the random oracle and so forth. And that's where this kind of distributional magic also comes in. Yeah.
So you're saying that H mu star can be maybe very, very close to some other solution of A times some C prime, and that's why it's equivalent to the SIS problem?
Can you say it again?
So the reason you said it was similar to or equivalent to the SIS problem is
Right.
because you can put it into a form of there's some vector that you can find C such that A times that Z is very close to 0.
Well, not exactly, because this is a uniformly random target in ZQN.
Right.
Right.
But then you can move it over and say that it's
Good.
very close to A times something else.
Close to A times something else. No, you have to move it over in a different way. Okay. So, but my hint to you is just move this over to the left side. Okay. That's my hint. I'll say no more. Anyway, this is kind of the high-level security argument for this thing. All right, so in order to forge, you break SIS, and you can kind of turn that intuition into a formal proof. Okay, so this is the abstract high-level description. It's actually been implemented in practice, and then earlier this month, NIST announced they're going to actually standardize this scheme based on this idea and a bunch more really nice ideas. And then they also are standardizing dilithium, which, does anybody care about practice? I can save us some time. Yes? Okay, good. All right, so I won't save us some time. Okay, so Falcon is one that follows this framework, and then dilithium I'll say in another moment. So many refinements to the 2 main components of what we've seen. The first main component was you have to generate this hard lattice together with the trapdoor, right? And that was one kind of black box that I didn't talk about. There have been now many algorithms that basically do this in some form or another. The ones in blue have this worst case hardness guarantee associated with them. And the ones that aren't in blue, they seem to be fine. They seem to generate a lattice that's hard to decode, but we don't really have a proof of that. And if you could mess up and end up generating lattices that are easy, right? So the reason we like worst case hardness is that we know that if you stick to that distribution, it's a hard distribution of instances. Right? So the question here is it really legitimately hard to decode within the threshold, the required threshold, on the lattices that are produced by these above methods that don't have the worst case guarantee? So you have to resort to cryptanalysis, basically, or find a different kind of proof to support it. So that would, that's a nice kind of research area that you could think about. And then the second component is the signing or the Gaussian sampling procedure. And that also underwent a bunch of improvements. And the Falcon scheme has a really nice procedure that will sample from that nice-looking Gaussian using the trapdoor that it produces. OK, so those are the two components. And yeah, as I said, the Falcon got the smallest key plus signature size of all the post-quantum signature candidates. And verification is really, really fast. It's a very simple computation. You basically do public key times signature equals, does it equal the hash or not? And is the signature short? And that's all you have to test. So it's screamingly fast to verify. OK, so that's the picture. And then dilithium, I shouldn't say finalist anymore. I should say selection. OK, that's out of date. This uses a kind of different approach that Lubashevsky initiated called Fiat-Shamir with aborts. It has the same kind of ultimate goal, which is to be able to sign without leaking secret key information. Okay, it does so in a very different way using kind of post-selection or rejection sampling. And that makes the signing algorithm extremely simple. You don't need to do any fancy Gaussian sampling or anything like that. So that's a really nice advantage of it. But the items are bigger. The public keys are bigger. The signatures are bigger. And it's also kind of relying on a little more non-standard hardness assumptions. In particular, and this raises the question, or calls back to the question you asked about other norms. So dilithium assumes, rather, that some form of SIS is hard where your solution merely has to be somewhat smaller than Q in the L-infinity norm. Okay? So every coordinate of your Z solution has to be maybe less than Q over 10 or something like that, right? So it's allowed to be quite close to Q, just not all the way up to Q. And every coordinate could be that big. So in particular, the Euclidean norm is actually larger than Q, right? It's like Q times square root of the dimension, which is beyond what's supposedly easy to get. But because it's the L-infinity norm, we don't know how to break this. But we also don't really have any proofs that support this. So could you extend the worst case hardness proof to something like this? Maybe. I don't know of I don't think the existing proofs easily adapt to that. Is there some attack? Is there some quantum attack? This is a good question. And then this will come up, I think, tomorrow in the quantum random oracle model. The security reductions that we have are sometimes not very tight. And that may indicate either some real gap, right, in security, or it may just indicate our proofs aren't good enough yet, and we need better techniques to get tighter proofs. So those are two kind of, I think, very interesting questions. I don't know how much insight I have into them, but they're nice questions nonetheless. Yes? Oh, yeah, great question. So the one I showed, the GPV signature scheme, we do have actually a tight security proof in the QROM for it. So that's nice, right? You can get a tight security guarantee. For dilithium style or Fiat-Shamir with aborts, we depending on the parameters, we sometimes have a tight one. In the real world parameters, we don't have a tight security reduction in the QROM, which is a bit, it's a bit of an interesting situation. OK, so some nice research questions have arisen from the kind of more practical efforts that have been done on here. OK, so I think that's all I have to say about primarily about SIS and signatures. So any general questions about those before we shift gears a little bit? OK, so let's now go to the second part of the foundations, which is the LWE, learning with errors, family of problems, and how that can be used to get public key encryption and encryption-like primitives. So this is another problem. It was introduced by Regev in 2005. He called it learning with errors. And as before, we still have our ZQN. So we have our dimension n and our modulus q. But now we have an extra character has entered the chat, which is the error distribution. Okay, so we'll see where that comes in. But the LWE problem can be stated as follows. There is a secret, okay, a secret vector S in ZQN. And your goal is to find it. Okay? Of course, you get some information about it. What you get about S are these noisy inner products, these noisy linear equations. So what that means is you get a uniformly random A1, and then the inner product of S with A1, modulo Q, but some error gets added to that inner product. Okay, and the error is drawn from the error distribution, of course. And then you can get another equation generated in the same way, and another, and another, and another. And you can have many of these. You can have as many as you want, or as many as the crypto system will give you, but that's what you get. So your goal is to find S when, for example, the errors are, again, Gaussian looking, for example. Okay. So just to kind of give you a flavor, the errors are a lot smaller than Q, okay? But they're not too small. They're maybe like square root of the dimension or so. Okay. And a term I like to use is the error rate. So the error rate, which is often called alpha, is just the size of the error divided by Q. Okay, so if you think of ZQ as a big cycle, like the clock, right? The error maybe is between 10 p.m. and 2 a.m., something like that, right? So which is 1/3 of the clock, right? So the error rate's about 1/3, and so it's some small fraction of the overall cycle gets added to every inner product here. Okay? So just to check your intuition here, suppose we didn't have the errors. Okay, then what could you do? Can you solve this problem? Yes. What would you do to solve this problem? Gaussian elimination. Yeah, you just do some linear algebra, right? So you'd get enough of these, maybe n or 2n of these or so. Eventually, they uniquely define S, and you just do a matrix inverse to solve for it. The problem is, and there's no errors on this side, so you can still come up with your matrix inverse over here. But the problem is these errors here, when you apply the matrix inverse, they just kind of send the answer all over the place, right? You can't recover the answer so easily. Okay, so as before, we're going to present this in a more compact notation with matrices and vectors. So we have our same A vectors, and we're going to, again, put them into the columns of a matrix A. But now what we have is the secret is multiplied on the left by the matrix A, and then there's an error vector, which consists of all the error terms. Okay? So yeah, if this makes sense, the secret is now a row vector. We transpose it as a row vector, and it gets multiplied by each of the columns, inner product with each of the columns of A, and then an error vector is added to that, and that is your vector of B terms. Okay? So the goal is to find the secret given this A, and then S times A plus noise. Okay? Another form of the problem is the decision problem. So the decision problem is not to find S, but to merely distinguish whether some A-B pair is generated in this fashion or is just totally uniform and independent. Okay? So here, B is close to a row combination of A up to some error, and here B is just uniformly random independent. There's no secret, there's no error, there's no nothing. And so all you have to do here is to determine, was I given something of this form or something of this form? Right? So that's potentially an easier task when you just look at it syntactically. Right? You don't have to solve, you just have to recognize. OK, so just as with SIS, LWE also has a really nice a combination or sequence of reductions that justify our belief in its hardness. So starting from, should I start from left or from right? I'll start from the right. We'll be able to build a lot of cryptosystems, countless cryptosystems by now, under the assumption that LWE decision is hard. Okay? So you design a cryptosystem and you prove by reduction that you can't break the cryptosystem unless you can solve decision LWE. Yes?
What's the difference between like solving this and Simon's problem?
And whose problem?
Simon's problem.
Simon's problem. Can you remind me of Simon's problem?
Basically,
Oh, no, I think I know what you mean. Simon's problem, the input is a quantum state, is it not?
yeah, it is.
Oh, but then he's telling me no, it's not. Okay, can you remind me of Simon's problem?
So, given a function f, this n is like distinct,
Mm-hmm.
there's some unknown as values and distinct for all x and y that are distinct. After x equals after y, then only x not sufficient.
It's hidden shift problem. Yeah, hidden shift problem. Good. Yeah, superficially they look similar. They're actually quite different in terms of what we can say about them. Let's see. I never came up with a really sharp answer for the difference between them. Yes.
One reason is that Simon's problem only works over finite field.
F2?
Right.
Yeah, I'm not sure that that's inherent to it though. I don't think. Yeah, I don't think F2 is intrinsic. John, do you have a? Yeah, so you're not evaluating a function. You're not like given a black box that you can query or anything like that. You're given passively, drawn samples that are not under your control, right? They're just generated and given to you. So that's one pretty important difference. In fact, there are some reductions that sort of allow you to reduce LWE to a hidden shift problem, but they incur a very large blow up in the parameters. And so even though you have a sub-exponential problem, a sub-exponential time algorithm for hidden shift, in some cases, the parameters blow up so much that it remains an exponential time algorithm in the original parameters. So yeah, but I can tell you more about that offline. Okay, so LWE's hardness. Okay, we're going to base a lot of crypto on the assumption that decision is hard. But in fact, if decision is hard, we can prove if search is hard. Okay, so even though the two tasks here are quite different, if you can solve decision, you can solve search via reduction. And there's actually a classic reduction from '93, and you can generalize it to these larger queues and a lot of different parameterizations here. And then the most kind of interesting and meaty part of the chain here is that if you can solve search, then you can solve worst case lattice problems. You can solve lattice problems in the worst case on n-dimensional lattices, and that reduction is quantum. Okay, so what this means is if you have, let's say, a classical algorithm for search, LWE, you can convert it into a quantum algorithm for these lattice problems. Okay, so the reduction itself is quantum, and therefore, under the assumption that these really are hard for quantum in the worst case, that makes this hard also for quantum, but for classical in particular. Okay, so based on this chain, we can say we have fairly decent confidence, at least, assuming these really are hard for quantum. We can now have evidence for the hardness of LWE. Okay, and in fact, you can remove the quantum here at the expense of substantially worse parameters. People don't like to use those parameters, but you can do it. So for the most part, for the kind of LWE that we like to use, the quantum reduction is still kind of the best we have. Okay, so that's the evidence for hardness. Really lovely papers and sequences of works here. But let's see why LWE is also a lattice problem. So just like SIS was, in fact, it's like a dual lattice problem to SIS. In more precision, it's actually it involves the dual lattice of the SIS lattice. Okay? So as somebody here anticipated, let's now let L of A, no perp anymore, right? L of A is going to be all the row combinations of A, right? So any Z vector that is some secret times A, or some S vector times A, and that's, again, going to give us a Q-ary lattice. And the LWE problem is I give you A, defining this lattice, and I give you B. B is close to a lattice point, right? It's a lattice point SA, but with some error added to it, right? Some perturbation. Okay, so given this perturbed lattice point, find the secret. Or alternatively, distinguish, in the decision case, it's distinguish between a perturbed lattice point and just a random point out in space. Okay? And you can actually, it's a little exercise to show that this lattice is the dual of the SIS lattice up to some scaling. Okay, so this LWE problem also goes by another name called bounded distance decoding. And the nature of the bounded distance decoding problem is that you're given some target point that's guaranteed to be not too far from some lattice point. Right? So here, the amount of error is small relative to the kind of shape of the lattice, relative to the density of the lattice, and the goal is to find that nearby lattice point. Okay, so LWE is an average case instantiation of this bounded distance decoding, right? Where the lattice A is random and the error is Gaussian, and that's what you're given. Okay, so any question about this so far? I just want to mention the core theorem that Regev proved, and it's the core of the reduction, is he shows that if you can solve BDD to some alpha fraction on a lattice L, then you can quantumly sample short lattice points from the dual lattice L star. Okay, so that is, if you can solve this thing, then you can sample from that nice discrete Gaussian I showed you before over the dual lattice. And sampling from a Gaussian in particular is sampling short vectors from that dual lattice. Okay, so the reason I bring this up is it's probably my most favorite and insane-inducing problem, which is to dequantize this theorem if you can. Okay, this step is inherently quantum, but if we could come up with a classical procedure that did the same job, we will have kind of solved the most important open problem related to LWE, I think. Okay, you don't have to dequantize this theorem. In fact, I don't want to bias you. I don't want to lead you down an impossible road here. If you could do this, it would, kind of be the silver bullet. But no, I don't think anybody has a good idea of how to do this. You might be able to dequantize this theorem in a different way, or dequantize this overall reduction in a different way, rather than doing it this way. Yes? Does it have? Oh, the implications, it would have many, many applications to theory. So we'd have a stronger hardness for LWE, right? We'd have a stronger hardness theorem. You wouldn't have to rely on an assumption about the quantum hardness of lattice problems. Everything could be classical, right? So, I don't think it would change the way anybody works with LWE in practice, but it would give us that much more confidence. Okay, so LWE since 2005, I guess it's been like 17 years now or something. Super versatile, built hundreds of cryptographic constructions from LWE. All the basic kind of bread and butter cryptographic objects like public key encryption, oblivious transfer, chosen ciphertext secure encryption, if you know what that is, pseudorandom functions, basically all the kind of ordinary tools in crypto. And then we can do some more exotic things like identity-based encryption and non-interactive zero knowledge. And these things are more complicated. And then we have these holy grails as well, like fully homomorphic encryption and lots of fancy stuff that you may not have heard of, but just on and on and on. So a lot of great stuff. And then these tests of quantumness also, these new protocols for quantumness that are out there, and lots of great things. You name it, they all have, they can be done with LWE. So it's really nice. I'll just show you kind of the most basic construction of public key encryption. Okay. So public key encryption, it'll work like this. Alice will again be the one generating a public key, and Bob will be encrypting a message to her. Okay. So let's suppose that there's some matrix A that's up in, available to both of them. Alice could choose it herself, or we could just choose it once for the whole world, and everybody could use it. So that's why I put it up here in the cloud. Alice is going to generate a secret key and then publish her public key. Okay, so what she'll do is she will choose a random LWE secret R, and she'll make it short. So she'll choose it from the error distribution, to be specific. She'll choose R from the error distribution, and she will do R times A plus some noise. So the noise is indicated by this approximation. So she'll do R times A plus some noise, and that is her public key U. Right, so her public key is U. And now Bob would like to encrypt, let's say, just a bit to Alice. Okay, so Bob's going to encrypt a bit in the following way. He will choose, again, a vector S, also short from the error distribution. So he's going to choose this S, and he's going to send A times S plus some noise to Alice. We'll call that V. Right? So actually, they're kind of both doing roughly symmetrical things here, just Alice multiplies on the left, Bob multiplies on the right. Otherwise, they're doing the same thing. OK, so Bob does this, and then he, well, from this point on, they actually have implicitly agreed to a secret key between them. So they can agree on a secret value, and let's see how. So Alice will take her secret key and multiply it by Bob's public V here. So if we just expand this out, we have R times V. Well, that's like R times A times S. Right? It's not exactly that because of this approximation. But this is hiding some error. And so what we're hiding here is R times the hidden error. Right? R is short, the error is short. So when you take their product, it's still pretty small. Right? So R times V is approximately R times A times S. And we'll call that result K. That's the secret key. And the same thing over here. Bob takes Alice's public key times his own short random S. And that looks like R times A times S up to some small error, relatively small error. Okay, so they both have a value that's approximately equal to K. And they can use this to now send a secure bit between them, for example. So Bob can send a bit by taking K and adding either adding 0 or adding Q over 2. So kind of sending it to the other side of the clock or leaving it on the same side. So if Bob sends this over, Alice can just subtract off K and look at, oh, is this close to 0 or is it close to Q over 2? And that indicates what Bob's bit was. Okay, so that's the basic idea behind the encryption. It looks a lot like Diffie-Hellman, if you're familiar with that. But it's got this noise in it. OK, so why should this be secure? I'll just give you a brief explanation of why this is secure. So suppose we have some eavesdropper who sees everything that goes over the wire, right? So the eavesdropper sees the matrix A, sees Alice's public key U, and sees Bob's V, and sees the C as well. Or if you prefer, we could say that he's either given the real K, or just a uniformly random K. Right? So what we're going to show is that all this stuff that the adversary sees is indistinguishable from just all random independent stuff. Okay. So let's see why. The first thing we're going to do is notice that Alice's public key is just an LWE vector, right? It's a LWE secret times A plus noise, right? So by decisional LWE, Alice's public key looks like a uniformly random U, right, with no underlying secret key at all. Right? So as far as the attacker can tell, this is A and U are both uniform and independent. Right? So that's step one. And then step two is let's observe now this V and this K. Right? What do we know about V? It also is random A times an LWE secret plus noise. And K is also random U times LWE secret plus noise. Right? So together, these are basically like n plus 1 LWE samples. Does that make sense? You get n samples here and one more sample here. But the nice thing about LWE is you can have a lot of samples. They all look uniformly random. Right? So altogether, we can say by invoking LWE again, these two things also look uniformly random, even given everything else. Okay, so this is the kind of high-level proof of why the adversary's view looks as if everything's random and independent and has no correlations among it. Okay, and that allows you to conclude kind of passive security of this encryption scheme. Okay, any question about this so far? Let's see. All right, yes? Yes. Yeah, it's public, uniformly at random. And one thing you'll notice is that this proof didn't depend on Alice picking it or Bob picking it or anything. So in fact, the whole world could use the same A if they wanted to. And there's an exercise about that on the sheet as well. So that has a number of nice consequences for other purposes. Yes? Yeah, so we've sent 1 bit, done a whole lot of work to send 1 bit, right? How could you send more bits? Also on the exercises, okay? So, but you know, if you just kind of look at it and understand what's happening in this proof, it shouldn't be too hard to kind of generalize, get some ideas of how you could generalize this and say, hey, actually, we could send a lot of bits if we just do something more, right? And I don't want to, of course you can do the whole thing over, right? You can just, for the next bit, do the whole thing over. No, you can reuse some stuff and not have to do so much new work for every bit. Okay? So we'll think about that whenever you wish. Okay, so that's the basic LWE. And then in practice, there is this Frotochem. And if you come up to me afterward, I'll explain the name. It's a historical, putting things historically out of order. So it was a bit of a joke at the time. But Frotochem was one of the NIST post-quantum crypto proposals. And it's working with like these kinds of concrete parameters. So we talked about Q before. Q is a 16-bit number here, or 15-bit even. And the number of dimensions is between 640 and 1300 and some. Right? So those are kind of an idea of how big these things are, or small in some case. And it uses a Gaussian error. The standard deviation here is like between 1.4 and 2.8. So what I want to highlight is that this is a good deal smaller than what the most like theoretical the theorems that are widely known in the literature are telling you to use. The theorems in the literature say, hey, you should use about root n as your noise width. So these parameters, nevertheless, do seem hard. Actually, they're bigger than most other schemes use. But nobody knows how to break them in any special way. But is that really the case? Or can you come up with some attack because these parameters violate what the proofs say? So in fact, they don't actually violate the proofs in a certain sense. If you inspect the proof and you dig into it, Regev full quantum reduction does not apply, but a component of it does apply if you kind of reverse engineer the problem to fit these parameters. So what you can show is that there's a reduction from this bounded distance decoding with discrete Gaussian samples to LWE, even for these more aggressive parameters. So I'll state the problem, and I think this problem deserves a lot more scrutiny, so that's why I'm bringing it up. It's an interesting problem in its own right. And here's the problem. So the problem is you're given a lattice, and there's some distance bound d, and the goal is to solve BDD to within that bound, given many discrete Gaussian samples of a certain width over the dual lattice. Okay, so the Gaussian samples have width, let's say, roughly root log n over d. Okay. And note that this width here is dependent on the number of samples. So you can either pick a very large n and get larger width, or you can pick a small n and get a correspondingly smaller width. Our best known algorithms that we know of can't solve this problem here. Can't solve it any better than not being given any samples at all. Okay? However, if you give slightly narrower samples, then we do know how to solve this problem. So there seems to be some kind of threshold phenomenon or threshold behavior where I can solve BDD to distance d if you give me dual samples of width 1 over d, let's say. Okay? But if I give you samples of this width, slightly larger by a factor of root log n, the algorithms break down and they don't work anymore. They don't seem to be able to take any advantage of those samples anymore. So what we're kind of working on here is like sort of just over the edge, just over the boundary of where these samples seem to be useful and how wide they are. But I don't know. I would not say with high confidence that I know anything about what to say about this. So it would be interesting to know, can we do anything? Can we prove anything about this problem? Is there anything to be discovered? I think it's a nice open question, unexplored. Okay, so is the question clear? I mean, I haven't defined everything here, but that's the nature of it. Good. So is this problem actually hard? What effect, if any, does the number of samples have? And then making this more tight as well, right? So this can be used to sort of justify or give us some confidence in these parameters up here. And the better you make this reduction, the more confidence it gives you. Okay, so that's LWE. And now I'd like to introduce an even more fruitful area for research, which is learning with rounding, so LWR. And the idea here is really simple, but it's quite unexplored. So what we're going to do is a variant of LWE, where there's no error distribution anymore, or at least not an explicit one that we sample from. Instead of sampling random errors, we're going to just generate the error deterministically by rounding off, or rounding or dropping low bits, rounding to a sparser subset. So the idea is if you think of the little ticks here as ZQ, right? So ZQ is 24, Q is 24 here. Then each of these regions has a rounding region, and anything close to 0 gets rounded off to 0. Anything close to 8 gets rounded off to 1. Anything close to 16 gets rounded off to 2. Okay, so the formal definition is we have some alternative smaller modulus Q prime, and we just define the rounded x as kind of rescale and round off. So this is the rounding from Z24 down to Z3. Okay, but of course we work with larger numbers typically. Okay, so interestingly, the LWE decryption, the encryption scheme that we just saw, in order to decrypt, you actually do this kind of rounding. You subtract off the key, and you say, is the result closer to 0 or to Q over 2? Here, we're using rounding to introduce error rather than to remove it at the end. So we can formalize this as a computational problem, the LWR problem, which is, as before, we have some secret, and then we're given these samples, A sub I, and inner product of S with A sub I. But instead of adding error, we just round off to the smaller modulus. Okay, so there's no error except for the implicit rounding error. And one way to see this is like LWE conceals low bits, right, by adding some random error to the value. And LWR just discards these low bits. So one theorem that we did show in the initial work here is that LWR is at least as hard as LWE, no easier, but with some pretty poor parameters, some not very realistic parameters. So if the original Q is much larger than the Q prime, okay, so the original modulus is much larger than the resulting modulus, the target modulus, by a factor of about 2 to the lambda, lambda being some security parameter, then you get a reduction from LWE to LWR, right? LWR is at least as hard for LW with error size E. Okay. Now, to give you an idea of why these parameters are not very satisfactory, first of all, the ratio of the two moduli has to be very big, right? More than 2 to the security parameter. So in particular, this means you're like throwing away at least lambda bits, right? You have to, the original modulus has to have enough bits that you can throw away lambda of them. And moreover, the original LWE problem has a very tiny error rate. It's like E over Q, which is 1 over 2 to the lambda. Okay, so it's a very small original error rate, and the smaller the error rate is for LWE, the easier the problem is. This LWE problem here, it has a very tiny error rate and a huge modulus, whereas this one has, you know, a moderately good modulus and a big error. So this is very lossy in terms of its parameters here. But it is something we can prove. And the heart of the idea is that if you just take LWE samples and you round off the noisy product, then with very high probability, this rounding is the same as if that error wasn't there in the first place. Okay, so rounding off an LWE sample actually generates a legitimate LWR sample with very high probability. Okay, and so in that respect, if you can break this thing, you can break this thing. Just take this, round it off, and run your breaker for this thing. Right? Okay, so you can show this, but as I said, the parameters are not too satisfactory. So let's compare that to what's actually used in reality. There were also some NIST proposals to the NIST PQC which rely on LWR instead of LWE, so Saber and entry prime. And their parameters look quite a bit different. They have a rather small Q prime and a rather large Q. So they don't throw away much. So that is, these systems have a very small ratio of Q over Q prime, like 3, or maybe 8, something like that. Certainly not 2 to the lambda. So they just round off a little bit. They throw off 1 or 2 bits or 3 bits of the low bits, and that's all. So as far as we know, according to attacks, this is secure. We don't know how to attack this in any special way, even though very few bits are being thrown away. But there has not been much effort, like actually, banging on that, especially from the point of view of quantum. So there might be some clever quantum algorithm which is able to take advantage of this. Who knows? So a lot of open questions about LWR. Is there theoretical support for small rounding? Maybe we can prove something about it. Maybe by going through LWE, or maybe we can directly prove some worst-case hardness that would justify these much more aggressive parameters that are currently not theoretically supported. Right? So you could try to prove hardness. You could try to find attacks. Usually going back and forth kind of helps. You get an idea here, and you transfer it to the other, and they go back and forth. Or could there be quantum attacks that can somehow exploit this small rounding? We don't know. Before it was mentioned Simon's problem. So it's an interesting idea to think about, could we take small rounding and apply some kind of reduction to Simon's problem? This has been done for things like LWE before, and could small rounding make that reduction more efficient so that the quantum attack actually works better? is a direction to consider. I haven't had any luck with it, but maybe you'll have an idea. OK, let's see. So we have about, how much time do we have? I can't do math. 10 minutes? Great. All right. So I'm going to conclude with a few thoughts about efficiency from rings. And there's a bunch of open problems here. If you like algebraic number theory or polynomials, things like that, there's a whole wide open field to think about. So the motivation here is that this SIS, LWE, LWR, they're all pretty efficient. In LWE, if you want to get one pseudo-random scalar, you just have to do an n-dimensional inner product and then add some error to it. That's pretty good. Like asymptotically, that's great. That's way better than any kind of factoring-based or discrete log-based thing. But in practice, these dimensions are pretty big, and this does take some time. And you can do some amortization tricks, but basically you have to do about linear work for every pseudo-random scalar that you produce. Okay, so for every random-looking value in mod Q, you got to do about linear work. And what this means is that the crypto systems kind of inherently have rather large keys. Okay, this thing is quadratic in size, right? It's got to be at least n by n, and this thing has got to be at least linear in size. And so it's going to kind of, no matter how you look at it, you have to do n squared work to encrypt and decrypt an n-bit message. All right, which is, I'm not saying this is terrible, but like we're greedy and we'd like to do better. Right? So let's just kind of imagine, what if we had some magical other operation instead of an inner product, right, giving us a single pseudorandom scalar? What if we had some magic operation star that gave us n scalars at once? Okay, or that we could use to generate n pseudorandom scalars at once. So some kind of operation A times A star S, which returned an n-dimensional vector, to which we could add error and get pseudorandom scalars. Right? That would be nice. And so we could, any place we had like a d by d chunk of matrix before, we could replace it by a single d-dimensional vector. So that would be great. So how to define this product operation, star, to actually get pseudorandomness, and how to make sure it's secure, right? We don't want to come up with something insecure. If you do the obvious thing, like use coordinate-wise product here, like the Hadamard product, this would be totally insecure. It's easy to break that. I didn't put it on the exercise, but add it to the bottom of the exercise sheet. Right? So show how to break LWE if you're using this coordinate-wise product. Okay, so the answer is not quite as simple as coordinate-wise multiplication, but it's not too much more complicated either. It's just multiplication, treating these things as polynomials. Okay, so if we define star to be multiplication in a suitable polynomial ring, like ZQX mod x to the d plus 1, then we can get a secure variant of LWE here. And the star operation can be very fast and very practical using like the usual polynomial multiplication tricks, fast Fourier transforms, and so forth. So, in fact, this is an old idea. This idea goes back to the very beginning of lattice-based crypto with the ntrue crypto system, which was used polynomials from the very beginning. And then it was given more theoretical support, first by Machancho in 2002, and now there's a whole long sequence of works that give theoretical support to this idea. So if this is what you should do. All right, so I'll define, just make sure you get that, okay. All right, so I'll define the problem in a very kind of oversimplified way, but just to give you a flavor. So we'll take the ring of polynomials modulo x to the d plus 1, and d will be a power of 2. So what this means is all these polynomials you can think of as having degree less than d, and when you multiply them, the degree grows, but you replace x to the d with -1 and x to the d plus 1 with -x, and so forth. So they kind of fold back on each other to be lower degree. Was there a question? No? OK. And then we can consider this modulo q as well. So yeah, as I said, these are polynomials of degree less than d, and you can do polynomial arithmetic very fast. And so the LWE problem, or like the ring LWE problem, or the module LWE problem, is we've got a secret which is now a vector of polynomials instead of a vector of integers mod q. And now it's vector polynomials mod q. And everything else syntactically looks the same. So we have the secret vector of polynomials. We are given random vectors of polynomials, and then the inner product between them. So the inner product is you multiply the corresponding polynomials and add them up, right? And then you add an error polynomial to the result. And that's one sample of your ring LWE. And then you can get another and another and another and so forth. OK, so if you think about it, each of these equations, each of these lines here, is really like D equations relative to this vector S as it's sort of a vector over ZQ. Right? They're the coefficient vector of S. This is effectively giving out D linear equations in S. But they're related, right? They're not independent. They're kind of correlated equations due to the polynomial structure. OK? And so overall, the secret is of dimension n, which is the k, the number of polynomials times the degree bound d. OK? So with this kind of syntactic framework, LWE, ring LWE, module LWE, all are just different parameterizations. LWE, you take d equals 1, so they're not polynomials, they're just scalars. Well, scalars are polynomials of degree 0, right? And then k is n. Or you can go to the opposite extreme and say we'll use a degree up to n and just a single polynomial as your secret, right? Or you can kind of mix, or you can interpolate between these two, right? Maybe you take a vector of 3 polynomials of degree n over 3, something like that, right? So it's kind of a smooth trade-off between how much structure, what degree polynomials you have. All right, and it's the usual thing. Decision is tell these apart from truly uniform, really random independent samples as before. Okay. So we have a number of theorems about this, kind of combining number theory, algebraic number theory, with the techniques that were developed for LWE, plain LWE. And they say the following thing. So as before, now it's much harder to show, but it still works. You can show that the decision problem is at least as hard as the search problem. And that's actually much more involved. It's not nearly as straightforward to do that, but it can be done. And then similarly to before, you can show that the search problem is at least as hard as some worst case lattice vector problems on what are known as ideal lattices or module lattices over your ring R. Okay? Again, this reduction is quantum. So what we have here is a more structured LWE problem, but it's at least as hard as a worst case problem over similarly structured lattices. So these are lattices that still have the same algebraic structure coming from R. It's not arbitrary lattices anymore, but still it's any lattice that has this ring structure. It's a module over this ring. Okay? So by kind of restricting our instances here to those that have the algebra, we can still prove the hardness of this more efficient structured problem here. Okay? So lots of open questions. This step here is quantum. And unlike with regular LWE, I don't think we have any meaningful dequantization of it. Not even like partial, not even with worse parameters. We just seem to have to use quantum here. Can we dequantize it? The classical reduction is not meaningful in this case, at least for the ring LWE case, just because this problem here, this gap SVP problem, is actually easy for the relevant parameters. So that's also a weird thing. One of the main problems we use in the unstructured case now becomes easy in the structured case. Some of the other problems still seem to be hard, so who knows? Secondly, how hard are these problems anyway, right? They come from algebraic number theory. They've been defined since the 1800s or even earlier. People have given a lot of attention to them. They're sort of some of the most interesting and well-studied lattices out there. But from an algorithmic point of view, are these instances actually hard, right? That's the question. And there is some work on this where the picture is different than it is for general lattices. So on the one hand, if you're looking for a polynomial approximation, we don't really have any significant improvement compared to general lattices. Okay, so for these small Pauli approximation factors, there's not really any known difference between the two problems. But if you relax your approximation to sub-exponential, like 2 to the root n, now we actually do have better quantum algorithms. We can solve that in quantum polynomial time, at least for certain rings. That's for ideals, but if you increase k to 2, those algorithms don't work anymore. Okay? So there's this kind of corner where, oh, we can do something here that we don't know how to do classically or don't know how to do on general lattices. And it's sort of a strange corner, and what's going on there, right? So yes?
Is it easy to kind of describe what is the special quantum magic that goes into the...
No, it's not easy. It's using quite a bit of, well, okay, let me say the quantum magic, it's not really clear that the quantum magic is so inherent. In fact, there's a small piece that's quantum, and I don't quite know how important that is. It has to do, I think, with recovering a generator of a principal ideal without regard to its length or anything like that. But there's a lot of very deep algebraic number theory going on here, as you might expect. So another open question is, actually, is the quantum really needed here, or could you just use classical stuff? So a lot of questions. K being 2 or more, I think there's no known difference between classical and between structured and unstructured. Yes.
So this is R for any R, meaning any figure of any number?
This theorem holds for any R, yes. These algorithms are only for specific kinds of R.
Because surely the difficulty, the ideal classical.
Sorry?
The ideal classical.
Yeah,
Whether it's a PID or not.
yeah, one would think that might matter. But it's not clear how much it actually does matter. A lot of them, these algorithms kind of manage to just blur out the class group, and it doesn't present an issue. So yeah, I mean, we could have a whole seminar on what's going on in this area. Yeah. And then one more thing I would add is this reduction says, search a ring LWE is at least as hard as these problems quantumly, but it might be strictly harder. And by all indications, it appears that it is. That is, if you gave me an oracle or a magic algorithm for this problem, we don't know how to solve this problem. Okay? At least not without changing the value of k, without changing the k. So I don't know how to reduce this problem to this problem. I only know the other direction. And so that's kind of interesting. There might be some strictly, some room to improve the reductions or seek reverse reductions. Okay, so that's a very quick overview of the situation here, but there's a lot of work. This is where the PhD comes in. Okay, so I think this is my last concrete slide. It's about these structured LWE problems in practice. So Kyber, Saber, Entru prime, all which made the third round, and then Kyber was selected as the kind of selection by NIST, are all using these efficient structures. So Entru, the Entru family uses a fixed rank k, so that is the secret is just one polynomial, And then they vary the degree of the polynomial. So if you want more security, you increase the degree of the polynomial. Kyber and Sabre take a different approach. They use a fixed degree polynomial, 256, I think. And if you want more security, they increase the rank. So the secret then has 2 polynomials, 3 polynomials, 4 polynomials, whichever. Right? And so it's kind of a qualitatively different approach. As far as we know, according to the cryptanalysis, the product, right, k times d, so the number of polynomials times the degree bound, is the sort of full dimension here. That's the main contributor to hardness. It's the main thing that controls the hardness. However, if you fix d and increase k, in that sense, there's less structure to it, right? Fewer symmetries, fewer linear symmetries in the lattice. So the question is, like, is there any actual distinction here, or is the n the only thing that ultimately matters? It's not clear at all. Right? The intuition suggests that increasing k should increase the hardness, maybe more than increasing d does. But that's just a guess. Second thing, that's another issue that came up also with Frodo. The theorems, the hardness theorems, require you to use error sizes that are on the order of square root n or even a bit bigger in all the coefficients of the error polynomials. But these systems use quite small error sizes, 1 or 2 or 7, something quite a bit smaller. And so again, we're in a situation where this seems to be hard according to cryptanalysis. We don't have any, we don't have any attacks that perform better than expected. But is there any theory to justify these choices? Or on the other hand, are there some clever quantum attacks that we could use? As mentioned again, Sabre uses rounding instead of random errors. Is there something we can do there, both on hardness or attacks? We really don't know. OK, so those are more open problems in the algebraic realm. OK, so to conclude, I hope I've convinced you that lattices are a really attractive foundation for post-quantum cryptography. We can do all the basic things, and we can do all kinds of great advanced things. And I didn't even talk about all the work that companies and research groups are doing on the advanced crypto side of this. But some really cool stuff is happening there. And we have a big, kind of a large gap between what the theory can show and what the cryptanalysis and best known attacks suggest. And over time, these have started to converge more and more, but they're still, not quite meeting up. There's some pretty significant gaps between them still. And so, while this is maturing, I think there's a lot of important work left to be done here and a lot of discoveries to be made. And so this is a nice success story where the theory comes in one direction, the practice comes in another, and they kind of meet in the middle, and a lot of really neat discoveries are made, and useful discoveries too. So thanks very much for your attention. I know it's been a long day, and happy to talk afterward or take questions.